to every single node. But it will probably be more like, okay, we offer this as a service to some subset of the network. So it will not be like we can do this for all of the nodes, but maybe for specific nodes. Let's say in this example, you have two quantum computers talking to each other, which then together control some machinery, just as an example. And so the question is also what we can do. We heard a lot about quantum cryptography, what we can do beyond quantum cryptography. And one of the things we already mentioned quite a bit was quantum network computing. I think that's definitely one of the very important goals. We also think about quantum sensing and something called the quantum enhanced random linear network coding. So basically how to condense information using, for example, the quantum randomness. And then we want to use cases where we don't really need these high data rates. If you really want to, let's say, compared to QKD, where we really want to actively encode things using ideally one-time pads, I suppose, and I'm not an expert in cryptography, so maybe I shouldn't talk about it too much. Anyways, you want to have a relatively high data rate in order because you needed continuously new keys. So the question is, can we do something which is within the reach of today's technology? Because as Mr. Lütgenhaus put it, if we want to implement this in 10 years, we already need to be able to do it in the lab today. So, so I think we need to look at what is possible right now, and yeah. So also we already talked about these quantum key distribution rates and where we are right now, and I think it's honestly for me quite depressing. I don't really see a big way forward of really doing this over a quantum network with multiple nodes in between. And yeah, so what the fundamental question now is, what I'm trying to get at today is how can we share quantum entanglement between multiple nodes, not just a single link. And so for example, this would be a fundamental building block of this kind of network. So this is the basic question I'm trying to address today, and also I'm trying to give some idea of what maybe could work after we get through a little bit of depressing stuff. And then also maybe talk a little bit about use cases. So I think we need to talk about quantum links. So we are talking in terms of entangled photon pairs. In this instance, of course, we can also think about different schemes, but I'm going to stick with the scheme for now. So we have an entangled photon pair source, and we distribute the entanglement by sending one part of the photons to Alice and another part to Bob, and then they can either store it in some quantum memory system or they do measurements on it. But in the end, we always need to do some sort of measurement in order to transfer it to some useful kind of data. Or we maybe would be able to use something like a Bell state measurement in order to transport this chain further by quantum repeater. But also there will be, it's also some sort of measurement from my point of view. Anyway, so the point is that we need this classical network. So the quantum link will not supersede the classical network. It will be just an additional component of this network. Now, so how this works, I mean, I tried to explain it already. So we send the entangled photons, then we transport them with minimal losses, okay? Then what the important point is in order to keep this a little bit general, we need to be able to do measurements in different bases. And at least this is my conclusion so far, that we will not be able to get rid of this kind of random base selection in the end. And then we need to exchange this information. And just this kind of a random base selection alone, if you just say that quantum link is perfect, this will limit our theoretical efficiency of the single quantum link to 50%. And of course, we have this kind of link efficiency, which Peter van Loock introduced, and the channel efficiency is still in there, which we didn't even consider yet. But if you take today's values, this would be very, very bad. So 50% looks quite good comparatively. But even if we just stick to this 50%, and look at beyond point-to-point communication, and let's say we have 5 entanglement nodes which we want to distribute the entanglement to, then we can do the math. And the math tells us, okay, even if we have perfect links, everything is perfect, the sources are perfect, the links are perfect, just this kind of random basis selection will limit our efficiency of this kind of 5 entanglement distribution to a factor to about 3%. And the reason is because because we are choosing a random base in all of them, and we don't if we don't somehow know what the others are selecting, then this whole efficiency goes with the nth power. So this is, I think, quite basic. The question is, okay, this means that even for small quantum networks, and in the end, we want to build large quantum internet, like the worldwide networks, right? So this is a very small network compared to that. Even for these networks, it really quickly diverges. So, and this is my opinion, at least fundamentally due to this kind of randomness, which is inherent in this system. And of course, if we come back to this link efficiency and channel efficiency in a second, these are even much worse today. So even if this is somehow circumvented, it will not solve the problem. And in any case, so we didn't consider all these other inefficiencies, which we can also talk about, of course. Anyway, so one thing I want to mention is, of course, this kind of long-range entanglement distribution, which has been talked about quite extensively already. So I just want to mention it, that just to make the scale clear, that if we start with 100,000 photons in Dresden and we want to transport it to Berlin, which is like 150 kilometers on the order away, then we end up with 1 photon on average. So, I mean, just this is a huge loss. And how can we possibly get around this is somehow a question. And of course, people are trying to address this in this QX consortium with this kind of quantum repeaters, which we also part of. But as we have seen, this is very, very challenging. Now, then let's look at real quantum networks. And the question is, from my point of view, as I explained, I would, for me, quantum networks need to somehow distribute entanglement. And the question is, do they do that? And the answer is no. These are chains of QKD point-to-point links. And so we have no entanglement sharing between these different nodes, even though this whole system is very, very impressive. And I don't want to downplay it. But in the end, I think it's not really what I would think of a quantum internet or quantum network. So, and we have these trusted nodes, which I think, if we, at least as a physicist, if I think about this kind of quantum security also, again, it's not really what we want. And so the question is, and do other people do this better? And no, again, I mean, it's just, these are all point-to-point links. In this an example from Toshiba in Cambridge. So, I mean, these are fantastic demonstrators, and don't get me wrong, but it's not, I think, where we want to go in the end. And so, from my point of view, quantum networks do not yet exist. And of course, the question is, how do we get there? So, let's go back to our little toy example here. So, we want to be able to do this kind of scheme. And so my idea is, and this is not new because I already inserted my opinion here a little bit in the discussion. Basically, my idea would be, okay, how can we do this? Maybe with graph states. And basically, we just replace this entangled photon source with a graph state source. And what it does is basically, what it allows us to do is we have these flying qubits which are connected to each other. That means, at least ideally, even when we lose 1 or 2 of these photons, we still have something left to entangle with. So basically what this means, we have a built-in redundancy in the sense that when we send each of these small chains to the receiving nodes, we have multiple attempts to do the entanglement. And this is basically the fundamental idea. And this gives us the ability to link these nodes together. And if we do the math, just with this very simple toy example, where we have 3 nodes and we use the same assumption as before, instead of 3%, we end up with 51%. mean, it's still not 100, but in principle, if you make these chains long enough, you could approach 100%. In any case, so if you want, from my point of view, this is also something, a very brute force way of doing error correction by just attempting it multiple times until we succeed. Of course, there is a couple of caveats here, and then, for example, which we also already discussed a little bit yesterday, that we somehow need to make sure that we shut off the system after a successful measurement. And how do we tell there is a successful measurement? So there's a couple of problems. Okay, but this is the general idea. And then the other thing is, which is I think also very, very attractive, is by doing measurements on these entangled quanta, we can actually change the network topology. And so we can decide how the entanglement is distributed in the system just by changing how we measure this graph state. Now, I mean, this is not a very new idea. People have been looking at this for quite a long time, I would say. And the graph state is really just a synonym for a lot of different kind of states, like cluster states, DHZ states, and so on. So there's a huge zoo of different possibilities. And what has been realized so far is basically this kind of DHZ state and a one-dimensional cluster state. So I will come back to these kind of experimental papers in a second. But so what else can we possibly use these graph states for? First of all, they are a basic resource for quantum computing. So you can do measurement-based quantum computing. Yeah, and you can do memory-free quantum repeaters. So this is the kind of graph state, let's say, theorists envision we could use to do this kind of memory-free quantum repeater schemes. And or we can, of course, also do quantum key distribution and to some extent quantum error correction. Now, this is all very nice, but what can we actually do in the lab? And so there's two main approaches so far. This is basically what I would summarize as multi-level systems. So we have a multi-level quantum system, and by using a very, let's say, clever way of manipulating these excitations in these levels, we can somehow, for example, produce a linear cluster state. This is what David Kashoni has done in Israel quite successfully a couple of years ago. And I think it's definitely one of the most impressive works on this topic. And then, of course, what Janbei Pan is working for this a long time. This is not the most recent paper. I think the last one is 18 photon entanglement. The problem here is a little bit, we have photon fusion. Photon fusion is a probabilistic process. And this makes it non-deterministic and very inefficient. But this is somewhat deterministic. I mean, also not completely deterministic, I suppose, but at least it could be in principle. Now, messed up. Okay, basically it's the same thing we're just talking about. Here's how this kind of photon fusion works. Basically, you just do Bell state measurements, and with this you can fuse the photons together. Okay, and the other, but how do we get to even more complex graph states? Is for if we want to avoid this kind of bad efficiency of the photon fusion process, is basically people have been suggesting to use molecules like quantum dot molecules, like John Finlay talked about, I think yesterday. And so I think this is a very, very interesting possibility to go to more complex graph states and to try to really produce this kind of resource. And the point is that the difficulty lies really in making the resource, and because once we do that, we can just by measurements, and this is, for example, explored in this paper, but there's Peter van Loock also showed some other examples. We can manipulate the structure of these graph states and therefore the topology just by linear measurements or linear rotations and then measurements. And we have this kind of applications I already hinted to a little bit. So we have this multipartite entanglement distribution and the quantum memory independent quantum repeaters. Okay, so what are the challenges for this kind of graph state? Of course, they are quite difficult to produce. This is basically the main challenge. while some progress has been made, so as I tried to point out. And then we have also a little bit of another problem. We still have an efficiency problem, but the good news is it's only the single photon efficiency which plays a role, but it still goes with the nth power. So in the end, in order to do something useful, we need to still do an n measurements and simultaneously, and that of course scales with the single photon efficiency. Okay, but it's still, I think it's still better than what we have if we just trying to brute force entanglement distribution with a certain fixed state. Let's say like a photon pair, entangled photon pair. Okay, anyway, so what is one of the applications people have been thinking about, or what we are thinking about also, Ricardo and I, sorry. So Ricardo and I have been talking about what we can actually do, and one of the examples would be to try to use this to provide a synchronization network. And there's a theoretical proposal basically which tries to span the whole globe with a sort of quantum GPS, if you want. So basically a network of very precise clocks which are linked together with this kind of sharing of entangled states. And basically the idea how it works is you have these kind of quantum clocks. And what are quantum clocks are basically quantum memories which give which you do a periodic operation on to extract a time signal. So what we need to do is basically distributed entanglement, write it to a local quantum memory which is coherent enough to so we can synchronize it again before it decoheres. So basically, if you think about anyway, so the point is that we want to use the quantum, the atomic clocks, for example, themselves as the quantum memory, or other way around, quantum memories as atomic clocks, and when you and then you basically just need to write to these quantum memories, and then you can already use them as your clock and to synchronize everything together. And the good news is, if you do that, in the end, you're really just limited by the Heisenberg uncertainty in the end. And with this, we hope we can somehow really enhance these 6G networks, because one of the problems is, and was Ricardo was somehow jumping over in his talk, is the kind of latency issues, and how do we get the same kind of clock signal at different nodes. And this is basically what we want to address first and foremost, but you can also think about other applications such as GPS or other ultra precise measurements which need this kind of time signal. In any case, what we also, of course, one of the other things what people are thinking about, not just us, is if we can somehow, generate this 2D cluster state, and if we can do that, people have shown that you can use it as a universal resource for quantum computing, for measurement-based quantum computing. And the good news is, once you have the cluster state, you really just need to do rotations and measurements, plus for some gates feed forward. But this really depends on the application, whether you need this kind of feed forward or not. I think Peter van Loek also addressed this already. And this is the key advantages. We are ultra flexible, and this can be very, very fast. So right now we are producing entangled photon pairs with gigahertz clock rates. And I think there is no fundamental limit. No, okay, not quite true, but there is we can still become much faster, I would say. In any case, even though I didn't show any data from my own work, I still want to highlight the people who are doing the work at the FW Dresden. And with that, I also like to thank you for your attention and hopefully a nice discussion.
Let's thank Caspar for the interesting talk. Now we'll ask the organizers question first. What do you think will be the main use case and the main challenge also for entanglement-assisted communication networks?
Okay, so I think the question is, when you say networks, do you mean point-to-point, or do we talk about networks in the sense that we have multipartite networks?
Feel free to choose.
So if I say point-to-point links, I think it's definitely QKD. Because that is something we can do today. So, and if you think about the near future, this is what we can do. If you really want to talk about networks, I think QP Day is out of the picture, more or less, from my point of view. So, because I don't see how to make it work. And so this is also why I'm trying to address here somehow, is to find alternative, at least ideas of what we can try to do with entanglement distribution without relying on these high rates. And I think this is the main point where also the challenges are, of course, the rates, right?
Okay. Which possibility do you see for quantum technology to contribute to the success of 6G networks?
I mean, that was what the talk was about, right?
Yeah, so